I have been given the responsibility of talking on antennas for millimeter wave applications. So, as you know, that the millimeter wave region, as such, it is from 30 to 300 gigahertz frequency band, and having very small wavelengths of from 1 centimeter to 1 millimeter roughly. Okay, wavelength range. So therefore, mostly this particular band has a lot of applications. In addition to what we see at microwave region, millimeter wave has a lot of applications, a lot of potential future application. Though we are already using it, I mean the area is not fully matured, but it is getting fully matured now. And then we have a lot of applications. So the one of the important properties, or rather the advantages of millimeter wave region is one is very large bandwidth. Okay, uh, typically the large bandwidth that we have, because it is several gigahertz. Uh, so one is the spectrum crowding problem can be resolved. As you know, the electromagnetic spectrum, they say it's fully crowded. Okay, it means we have got several applications, already, right from very low frequencies to low frequencies, then to high frequencies, then VHF, UHF, you know, and then EHF, SHF, then into we have this microwave region. So there are applications, which are occupied by the entire electromagnetic spectrum. So that's why people say that the electromagnetic spectrum is fully crowded. It means we have applications exploiting each and every small region of electromagnetic spectrum. So therefore, mainly for communication applications. So at the lower end, below this range that I am talking about, the 3 to 30 range that I am talking about, below this range of, there are several applications already. So people started wanted to exploit this particular region. Okay, and it is in gigahertz range. Let us say you take 1 gigahertz, for example, that is 1000 megahertz. Okay, in 1000 megahertz, if you take for each channel, if we video channel of, let us say, 5 megahertz. So in 1000 megahertz, 1000 megahertz divided by your 5 megahertz. Okay, that roughly becomes 200. Okay, 200 video channels we can actually transmit using a single carrier at gigahertz range. Okay, so like that, if you use for voice, because each voice channel requires only about about 6 kilohertz. If you take 3 kilohertz multiplied by two, now you see how many number of channels we can accommodate in 1 gigahertz bandwidth around the center carrier frequency. So therefore, so very large bandwidth is actually one of the important characteristics of millimeter waves, especially for communication application. That is especially at very high data rates if you go for digital thing. Okay, so similarly, because of the very short wavelength that we are talking about, of the order of few millimeters, so design of the antennas with very high directivity and a reasonably small size. Okay, so that you can have high resolution radars possible, and very compact guidance systems becomes feasible. And also millimeter waves, of course it is true with any high frequency waves. So they can travel through fog, and they can travel through snow, and also they can travel through dust. So therefore, much more readily used than infrared and optical waves. Okay, because optical waves may get even though frequency is in terahertz, optical waves, but they have issue with the fog or snow. Therefore, it is better, we use such millimeter waves of several, tens of hundreds of gigahertz. And finally, millimeter wave transmitters and receivers. Okay, we can integrate them into monolithic design. So it is possible to have the technologies of monolithic microwave integrated circuit called MMICs. Okay, so therefore we can have very compact and very inexpensive circuits can be built. Okay, right. So these are all the various advantages why people focus on millimeter waves and then try to exploit it for various applications. So in today's session, I'm going to talk to you on, some of these. In fact, I want to show you the current research that is going on in this area in building antennas, for specific applications. Okay, so the area is very vast area. In fact, even at NIT Warangal, we recently started working in the millimeter wave area. Otherwise, most of our research concentrated only in the microwave region. But we started, doing some research and have some papers published. Okay. All right. So before I go to the actual applications and show you the current research and some of the antennas that are made, I just want to spend few minutes on some of the theoretical details of how small antennas can be made. Because as I'm saying you that the wavelengths are the order of few millimeters, is it that that we can make antennas as small as we like? Okay, or is there any restriction on this? Okay, there is something called a small antenna theory that I would like to spend few minutes of my time on this. Then maybe show you the current research, some of the designs. Okay, usually people try to do a lot of research on trying to build smaller and smaller antennas. That means if I design an antenna for a given application, for example Wi-Fi, WiMAX or RFID, okay, usually the professors or scholars who do research in microwave and antennas field, generally their main focus is what compared to what other researchers have done. They want to improve it by some delta x. Okay, in terms of various parameters. For antenna, usually there will be so many parameters, like the beam widths of both the horizontal and vertical planes, and then 3 dB impedance bandwidth, and then what is the VSWR value and what is the return loss. Okay, and cross polarization thing. And if it is circularly polarized, then we find axial ratio bandwidth and axial ratio value. There are so many such antenna parameters. So when I'm trying to improve upon the research by the previous researchers, I always try to get a better design which can give you parameters better than what other researchers has done. For example, somebody designs an antenna with a bandwidth of let us say 1 gigahertz. If I design an antenna with 2 gigahertz bandwidth, much smaller than what the other research has done, then that is what I am contributing as my research to the antenna design. Okay, so therefore this particular thing is called antenna miniaturization. So therefore people try to build antennas as small as possible in the given in the given band of frequencies for various applications, for example. So it's a very interesting field. Okay, so therefore from the beginning what is generally desired, uh, sorry for that. Okay, what we want to build a very small and desirable very small and versatile antennas that are built. Okay, all right. So therefore, what is required as on today is actually is more multifunctional systems. Okay, and which require for your mobile terminals, including cell phones and then handheld and portable wireless systems. Okay, mainly for a very high speed internet connection, and short, especially for very long range application, and similarly for radio frequency identification systems. So these are all the applications where we require multifunctional antennas. In fact, people today try to design antennas, not antennas separately for all these applications, but antenna that can work for more than one band. That means if I design antenna, it should work for all these applications, RFID, as well as mobile, as well as for for Wi-Fi, WiMAX. It's not that we design independent antennas for various such applications. Similarly, we also have equipment for example, GPS, okay, which requires smaller antennas. Okay, so therefore, there are several of these applications now. We see a very continuous growth in the wireless devices, and it's a challenge for the RF community, or engineers who try to work in the domain of radio frequency systems design. Okay, so for example, if you see your current phone, you find here so many antennas, as you see here, antenna for a very high band, low band antenna, and so many things. Instead of that, we can have one single antenna, okay, which can serve all the purposes. What actually towards multi-band design we shall see. So electrically small antennas means the maximum dimension is actually less than lambda by 2 pi. Okay, they are called electrically smaller antennas, and in fact, the antenna which actually people started designing with dipoles, it started with that. Okay, so therefore, electrically small antenna mean that actually which satisfies this particular condition, where k is called the wave number, the lambda by 2 pi that I have talked about. Okay, and again the a is nothing but the radius of the minimum size sphere that can enclose the antenna. Okay, what I mean to say is that we cannot have smaller than this. That's what I mean to say. Okay, so for a given lambda that you are talking about, because lambda is decided by your frequency, okay, where a is the radius of the minimum sphere that encloses the antenna. Okay, so you build an antenna now, so therefore you have to find out lambda by 2 pi here. For k, you substitute lambda by 2 pi, okay, and find a in such a way that ka is less than 0.5. Whatever a that comes, that is a minimum sphere. Okay, so therefore the antenna should have a minimum size of a. Okay, that means from top to bottom it should be minimum size this much. That is nothing but no diameter, of course, that means twice of a is what I am talking about. So we cannot have an antenna smaller than that. That's a theoretical restriction that we have. Okay, so however, whatever the kind of research that you do, you can't physically build an antenna smaller than an antenna which satisfies this condition. This is called small antenna theory. Okay, that's a theoretical limit in antenna miniaturization. Okay, I thought let me give you this point so that you will understand the what is the lower limit of the size that we can have. Okay, so that they are called electrically small antennas. Electrically small antenna is Ka less than 1 generally, though we say 0.5, the theoretical thing. So therefore, it is now interpreted as an antenna enclosed inside a sphere of radius equal to, it is called 1 radian length. Okay, right? Such a sphere is generally called as a radian sphere. So therefore, even in millimeter wave also, we can build now antennas with very, very smaller in size. Okay. Yeah. So this slide shows you, generally the meaning of a radian sphere that I've talked about, and there is something called a near field up to that, and beyond which we are what is called a far field. So for all antenna applications, the transmission and reception has a use only when it is in the far field. Okay, near field actually we don't use. It's only a sustaining oscillating energy that we have, but only in the far field that any other antenna which receives the power from the transmitting antenna has to be placed. And for antennas, usually these are the various parameters that we have to keep in mind when you are designing them. Whatever it is, whether you are designing a HF antenna, or we're designing a VHF antenna, a UHF antenna, or a microwave antenna, or a mmW millimeter antenna. These are the essential parameters. One is size, the quality factor, the fractional bandwidth, the gain, and the efficiency. And of course, there are other parameters like VSWR, and then they are actually linked to this anyway. Okay, so these are the essential things that you have to keep in mind. Okay, when you are designing antennas. For example, radiation efficiency is given by theoretically radiation resistance by RA. Okay, where we have to consider also some loss into account. Okay, so usually losses are very prominent for smaller Ka values. Okay, so therefore the reason why I'm trying to give you these details is it is while handling smaller antennas is easy because we require less material, and then handling becomes because the smaller you go, more difficulties that you come across, essentially. Okay, it is inherent in all the radio frequency designs, because as the circuits become smaller and smaller, the circuit can be an amplifier, a circuit can be a filter, the circuit can be any integrated system that works at high frequency. Their dimensions are much smaller, and they are whenever they are comparable to the wavelength, then we have more and more problems coming into picture. So therefore, as you move to the high frequencies, the reason why we find a lot of deviation from the theoretical and from practical observations is because of these issues that we find at higher frequencies because of smaller size. So therefore, the circuit that you design will not work as per your predictions. Some may start leaking the energy, some may start unnecessarily radiating energy, because they become unintentional radiators. They become what are called unintentional radiators or unintentional radiating elements. Okay, so it is because of these several issues that designing antennas at high frequency is very difficult. Okay, so you'll have a lot of issues, a lot of trial and errors you have to make, and then yeah. So there are several factors that you take into consideration when you are choosing the material for designing an antenna for a given application. And because I know this one is actually based on this kind of an equivalent circuit that we should take, because antenna has this radiation loss, R loss will be there, and then radiation resistance, and then this antenna impedance. Okay, so typically when you feed high frequency energy here, high frequency oscillating energy for to be radiated. Anyway, it has to be only a sinusoidal energy that we have to feed. Okay, and and they should have a lossless, matching network, so that the antenna impedance ZA should be matched to the source impedance. Otherwise, you will not have effective, radiation from the antenna. Okay, so all these things are the design constraint that we should take. And also there is something called a quality factor for the antenna that we should take into consideration. Okay, and the power of this one, okay, energy. It's actually the maximum of energy of in the electric field and magnetic field we take. So therefore, the power input to the antenna is generally is PA. Then eta is your radiation efficiency, as I shown you in my last slide. This eta, okay. Then actual power that is radiated is actually so if my eta is 0.8, so I'm getting only 80% of the power that I generate is now only radiated. Okay, so therefore this eta is very important, is one of the parameters that we should find out when you are designing an antenna, what is its typical efficiency. Otherwise, there is no point in using an antenna whose eta is only about 0.5 or less than 0.5, because half of the power is getting lost. Okay, it's not an efficient radiator. Okay, so yeah, so Q factor is also related to the typical antennas, bandwidth. Okay, typically 3 dB bandwidth. If FC is my center frequency, okay, so it is Q is nearly is 1 over B, where B is your bandwidth. Okay, so this is another parameter, and also we have what is called fractional bandwidth. Okay, the bandwidth is okay. Um, Fractional bandwidth is generally the frequency range divided by the center frequency. Okay, so and as I've shown you, the Q factor can be related to uh, the bandwidth of the antenna. Okay, yeah, so that's actually called the fractional bandwidth. Okay, so these are some of the few general theoretical details on the uh, uh, antennas, especially small antennas. So this is actually a photograph that I am showing you, where you can see here a microstrip antenna integrated into a system. Okay, typically as you see here, this is a millimeter wave band. Okay, typically a base station antenna of a long haul system. Okay, now I'm just showing you this photograph just to impress upon you how the overall system looks like. Okay, so this is typically as you see here, this entire thing is actually millimeter wave circuit, okay, which takes a DC power supply, and there is an amplifier, low noise amplifier is there, and there is a power distributor is there, and then various connectors, filters are there, okay, and then there's a medium power amplifier is there, a diplexer is there to connect the receiver and transmitter, okay. So this entire system, as you see from the scale here, it occupies a size of typically one or 2 or 3 centimeters, okay, and integrated into this one. Okay, so this must be operating typically with a power of about 1 to 2 watts. Okay, all right. So this is how finally, once you develop a system, it looks something similar to this. Okay, and as you see, uh, a practical example that I wanted to show you, right? And as you know that most of the designs at microwave frequencies are millimeter wave frequencies, though there are very advanced designs at millimeter wave frequencies. But typically, we prefer microstrip as a design choice, though there are other advanced designs using other materials. Okay, there are some kind of a combination of polymer materials are also used to design antennas, but most designs are using microstrip based designs, but depending on the application, or depending on the application means, um, as you see, there are various wireless applications. So depending on the band of uh, interest, we have to choose an appropriate material. For microstrip designs, for the microwave and millimeter wave designs, so we have various materials available in the market. So some of you may be doing research in antennas, or some of you would have already completed your doctorate in antennas and microwave engineering. So they will know that materials like RT Duride is one material, and FR for fire retardant for and like that. There are various materials, okay, are various substrates that we get for designing microstrip antennas, and various thicknesses that we get. Okay, so therefore, typically you see a kind of a board like a backlight, not backlight. For high frequencies, we use FR4 based or RTDuride based designs with the substrate thickness varying. So the boards look like your printed circuit boards. Okay, but the thickness will vary. Okay. So for my typical microwave designs, while they may have a thickness of about 1 mm, 1.6 mm, sometimes even 2 mm also as a thickness of the antenna structures. But at high frequencies, as you go, the thickness will reduce to less than a millimeter. Sometimes you also get a foil type, okay, with a very thin substrate of a fraction of millimeter, zero point 0.1 millimeter, and zero point 0.2 millimeter, 0.5 millimeter, like that. Okay. So the advantage of using microstrip antennas are generally low profile. This is one advantage. Okay, because the size is less and the weight is less. Okay, and also sometimes they can be conformal. Conformal means what, so antenna can become part of the device. For example, if we have to build an antenna for a missile, okay, and if you take a board type of an antenna, it occupies some space and it requires a special arrangement. Whereas if you can bend the antenna, okay, if it is a board type, hard board type means we can't bend it. But if it is very thin like a foil, then we can bend it. Okay. So since usually missile's body is round like a cylinder, so therefore the antenna can be part of the cylindrical body of the missile. Okay. So therefore, when you can build an antenna, okay, which can be conformed to the shape of the final mounting structure, okay, then that is they are called conformal antennas. Okay, which can be bent. Okay. So anyway, there'll be various studies that they need to undertake. How much should be bending radius, and what should be the size and all that. That's a different story. But basically, microstrip antennas are suitable for all such. They can be conformal, and also easy to fabricate. Okay, easy to fabricate is another one. So they use a photolithography technique, like how we actually manufacture PCBs with the printed circuit structure etched on that. So similarly, antenna can be fabricated, easy fabrication with the process. Okay, now the process are well established processes, and also easy to feed. Okay, easy to feed. We can use a coaxial cable to feed, or we can use a microstrip line for feeding. There are various types of feeding mechanism that we use. Anyway, I mean, each and every feeding mechanism has got its own advantage. Okay, but mostly at microwave frequencies and millimeter wave frequencies, they prefer microstrip line feeding. Okay, of course, coaxial cable. There are different varieties of connectors that they use, very small and minute connectors. Using them, they feed the energy to these antennas, because once antenna is fabricated like a copper foil, okay, how do you feed the signal to it is a question. Okay, so for feeding that, we use microstrip line, or there is also called aperture coupling feeding, and probe feeding, and proximity coupling. There are several. There are about 78 varieties by which we can feed the signal to the antenna. Okay. So again, the type of feeding mechanism depends on what kind of an application that we are choosing. Okay. And each and every feeding technique also has its own advantages. Suppose if you want very wide bandwidth, a particular feeding mechanism is suitable. If you want, for example, circular polarization, left-hand circular, right-hand circular polarization. Okay. So again, there are certain feeding mechanisms which are suitable. Okay. So appropriate feeding mechanism will be chosen, through which the energy is fed, okay, to the microstrip antennas, which are very smaller in size, of the order of only few millimeters or few centimeters. If you go to micro, but if you go to millimeter wave, they are of only few millimeters in size. Very, very small, tiny antennas that we fabricate. Okay. And also another advantage of is easy to use, because whatever example that I'm going to show now of millimeter wave antennas for different applications are all made of mostly microstrip thing. That's the reason why. If not one layer, they use several layers of such a, microstrip, layers, okay, to get the desired characteristics. Okay, so we can also use this one as an array, okay, so that it can be easily integrated with the other antennas. Okay, and also the patterns are somewhat hemispherical mostly. It's not a omnidirectional, but it is hemispherical because mostly the radiation is from the board or from the antenna to the upper surface. Okay, and at 6 to 8 dB typical directivity that we can obtain. Okay, some lines are coming. Okay, I don't know. One minute. I don't know. There is a line here, unnecessary. I don't know why that line came. I'm sorry for that. I'm using. Maybe I'll just. Oh, it is there on all the slides. I don't know how it has gone. There is a red line that is coming. Anyway, sorry for that. I think suddenly it came into all the. Just give me a second. I'll just discard because I'll just discard the annotations. Okay, so I'm sorry for that. There's a red line coming here. I don't know why. Okay, all right. Let me go ahead. Okay. So, of course, in addition to these advantages, there are some disadvantages as well due to the due to some other factors. One is generally we get low bandwidth. Okay, but of course there are several ways by which the bandwidth can be improved. There are several techniques by which the bandwidth can be improved, and efficiency may be lower. Okay, just give me a, maybe I'll just, sorry for the I'll just maybe close this. I think yeah, now I got the reason why it is. I think it is not, this red line is not because of me. I think the organizers have to disable the annotation. I think some of the users who are listening my lecture, they are trying to annotate the screen. That's why that red line is coming. What I see here. Okay, I don't know whether you are able to see that. It's not from my side. Now I got it. Okay, so maybe organizers kindly disable annotation option in your, I think it will be somewhere. Let me check. Yeah. Pause recording, disable. Yeah, this one, disable. Can you see the screen? In the three dots, there is a disable participant annotation. Can you do that, please? From the organizer. Yeah, I have disabled it now. Okay, fine. Okay, fine. Let me go ahead. So this red line is actually from some participants. Okay, all right. So the generally low bandwidth is one of the disadvantages, and also the efficiency may be lower. Uh, Efficiency may be lower than the other antennas generally because the antenna is actually made of a circuit board generally, which actually cannot handle very high power, and also mostly when antenna is fully made of metallic structure with a lot of other things, that usually it will have more efficiency, but here being very small in size, typically it is less. Okay, efficiency is less, but of course mainly due to this dielectric loss, and other one is surface wave loss. These two are the things. Okay, so generally this dielectric loss becomes more severe for thinner substrate. Okay, so this is one issue. Okay, thinner substrate generally, what do I mean? In fact, for all high frequency, especially millimeter wave frequencies, we prefer thinner substrates. Okay, we prefer thinner substrates only because of the conformal nature, or you want to mount into a particular, application, into this one. So, but thinner will have this problem called dielectric loss. That is one thing that we have to keep in mind whenever they design the antennas for microwave or millimeter wave application. And of course, the second one called surface wave loss that I'm showing here, it becomes more severe for thicker substrates. Okay, unless air or foam is used between the antenna layers. That when you stack them up, okay, we have to use some of these layers. But when you want to have a very thicker substrate, no, but thicker substrates have some advantages in terms of stability of the antenna, sturdity of the antenna. But thicker surface have this surface wave loss. So therefore, we have to make a compromise between what actually the application that and how you want to handle. And some of the basic principles of operation when you design an antenna. Typically, all the microstrip antennas, they work based on what is called a resonant cavity principle. Okay. Because I have the in the microstrip antenna, typically the bottom will have a ground plane. On top, we have the that means we take a printed circuit board with a copper plane on the bottom and another copper surface on the top, which is actual antenna, which radiates signal towards upper surface. And bottom generally will have a ground plane. Okay, so it is like we have a substrate between the two copper surfaces. So therefore, we assume that there's a kind of a cavity, rectangular cavity formed, or a kind of cavity formed between the two conducting walls. Okay, so that's why it is called a short circuit, a permanent electric conductor, and then a permanent magnetic conductor. Kind of a principle that is being used there, so which actually radiates the signal into the free space. Anyway, I will not go into the theory of microstrip antennas now, but that's how it works. Okay, so in a cavity, only certain modes allowed to, like, because it's like a waveguide, there are some propagation modes that exist between the two walls, and then energy gets radiated when you feed to the radiating patch. Okay. So therefore, if the antenna is excited at a resonant frequency, usually very strong field is set up inside that cavity, and a very strong, current will be there on the surface of the patch, which actually radiates the signal. Okay, so therefore, it produces a very significant radiation. That's typically a good antenna. Okay, so generally, as the substrate thickness gets smaller, as I told you, the patch current, the patch current radiates less due to a principle called image cancellation in the layers, the top and bottom conducting surface that I'm talking about. Okay, but however, Q of the resonant mode also increases. Okay? So therefore, the patch currents are stronger at resonance. So therefore, when you're designing an antenna, we have to actually feed the antenna at its resonant frequency for it to radiate more power, okay, into the space. Okay, so that's about the general background theory that I thought I'll explain, so that the antenna designers take care of all these issues into consideration when they are actually designing antennas for various applications. Okay, all right. Okay, so now when you come to the millimeter wave antennas, mm, in fact, I thought I'll show some of the photographs of the antennas, but anyway, it doesn't matter. Millimeter wave antennas, while we have as I explained to you already, antennas are designed and manufactured for various bands of application. Okay, and these antennas, they vary in their shape, in the size, and in terms of the materials that we use, depending on the application. Okay, so therefore, you see various structures when you look at actual antennas, you see various structures. Some are like, rod antennas, okay, like your dipole antenna that you see for cellular communication. Okay, cellular application like a 2G application or a 3G application. Okay, you would have seen, cell towers around you where you see a tube light like structure, big ones. Okay, they are basically dipole antenna. Sometimes you see a parabolic antenna, sometimes you see a horn shape antennas, sometimes you see a dish antenna. Okay, these are the various shapes of the antennas that are manufactured for various applications. Okay, so what I mean to say, depending on the band of frequencies, all these vary. Okay, when you come to the millimeter wave frequencies, that is subject of today's interest. Okay, mainly while the previous antennas that I talked about, we use for VHF UHF communication. We use monopole antennas, and we use the horn antennas and dish antennas. In radar application, we use them. Whose actually size varies depending on the frequency band. Okay, if you see on the satellite, typically you find antennas of very size of maybe 1 feet diameter to about 1 meter diameter also. If you see typically satellite earth station antenna, if you remember any of the photographs that you have seen of satellite earth station, I'm not talking about satellite antennas on the satellite. I'm talking about earth station antenna, which is on the ground. Typically, earth station antenna will have 30-meter, 40-meter diameter, which communicate to the satellite. Very huge antennas. Okay, so therefore, what I'm trying to tell you is that these antennas, which are manufactured for those applications, they actually vary. And again, as I told you, that microwave antennas can be lens antennas, horn antennas, like that. And we also have microstrip antennas, as I explained to you, which can be designed and manufactured for microwave applications like Wi-Fi, WiMAX, RFID, okay, and UWB application. Okay, so in these applications, we use all these microstrip antennas. Now, when you come to the millimeter wave antennas, which are very smaller in size, of again various designs and various shapes, they use in mostly in cellular and satellite phones, satellite phones, and also for long haul line of sight communication links. Okay, okay, I'll show you some of the antennas which are designed, smaller antennas of few centimeters and few millimeters in diameter. Okay, okay, all right, but they actually have shapes and forms in some of these categories. One is a surface wave and the leaky wave antennas. Okay, this is one category based on millimeter wave waveguides. Millimeter waveguides are actually very small transmission lines which carry the signal of the order of several tens and hundreds of gigahertz. As I told you, from 30 to 300 gigahertz. Okay, so mostly the bands that we talk about here, are we talk about K band and Ka band. We talk about K is actually 18 to 27 gigahertz, and Ka is K above. A stands for above. Ka is actually 27 to 40 gigahertz, and again we have got V band around 60 gigahertz, and W band is there. So they're all high frequency bands into tens and hundreds of gigahertz. Essentially, the millimeter wave frequency range. Okay, so in this category, we have taper dielectric rod antennas. That means we take a dielectric rod, and then the antenna is manufactured around this dielectric rod, and then periodic dielectric antennas and uniform waveguide leaky wave antennas. These are the categories of, these are the forms of different antennas. Okay. You know, for the millimeter wave applications, which works on based on surface wave or leaky wave principle. Okay, but these materials are what are used, and similarly, microstrip is also used. As I told you, they are called microstrip resonator antennas at millimeter wave. Okay, In this, we have microstrip antennas with electrically thin substrates. Okay. Uh, See, it is called electrically thin, not physically thin substrates. Okay. So it means to say that the lambda of the frequency and the substrate thickness, okay, these are comparable. They are called electrically thin. Electrically thin means the thickness T that I am talking about is much smaller than the wavelength. Okay. So they are comparable. Similarly, we have microstrip antennas with electrically thick substrates, and also another category called holographic antennas. So these are used at millimeter wave frequencies based on microstrip designs. Similarly, there is also another category called integrated antennas. Okay, integrated antennas. Again, there are categories called taper dielectric rod antenna with integrated mixer diode. Okay, these are actually used for the active applications, and similarly, monolithic microstrip antenna phased array. That means we build an array antenna. Instead of one element, we will be having several elements. I think I have some array fundamentals which I'll show you now. So they are actually made of monolithic microstrip antenna, which are designed and fabricated with special techniques. Then we have integrated near millimeter wave imaging array antenna. They are quite advanced, antennas that they are designed for millimeter wave application. Especially main applications are, one is a 5G cellular application. I'll show some slides to you now, and also for satellite application and for long distance, communication, especially 5G, mostly 5G applications. 5G and all the coming generations, 5G, 6G, and so on and so forth. Okay. So as I explained in the previous slide, as I told you, the long haul line of sight, they are actually called millimeter wave links. Okay. So mostly millimeter wave radio links are the dominant application. They are called backhaul links, are mainly used for the telecommunication infrastructure, particularly, as I told you, for the cellular wireless access. Okay. Okay, cellular wireless access in very dense, urban areas. Okay, very dense urban areas where, I'll just keep it down so that your slide will not get abstracted. Okay. Uh, okay. Uh, Okay, fine. So one example is your typical 139 Gbps, 139 gigabits per second. You see here, very high capacity, compact size link with a typical distance of coverage as 1.5 kilometers. Okay, which uses actually a kind of a MIMO setup, multi-input, multi-output antenna structure in E-band. E-band is 70 to 80 gigahertz is E-band application. Okay, this is one example where millimeter wave radio link is exploited for typical communication link. Okay, so this can be, as I told you, cellular application, or it can even be a military application. Okay, so implementation of antennas for such range of 30 to 300 gigahertz, it shows there are certain challenges. Okay, especially from the hardware perspective, it's not that easy to manufacture antennas and integrate with the systems, but it poses several challenges for designing. So especially from the hardware perspective. Okay, so these are some of the challenges that are generally seen. Okay, one is millimeter wave front end modules. Generally, I mean, I have shown you a photograph just now. They are actually called front end modules at the transmitter. Okay, like low noise amplifier and filters and band pass filters and medium power amplifier integrated. That is called a front-end module. Okay. So usually they are much costly than the modules that operate microwave bands. Microwave band is actually, less than 30 gigahertz. Okay. But now these things cost more. That is one challenge. Okay. It is mainly, the reason is mainly active devices as well as passive devices are used here, which are quite, expensive. Okay. For example, passive components such as filters, okay, and also the microstrip antennas that you fabricate, they become smaller in size. Okay. And also whenever you want to build very smaller things of few millimeters in, dimension, you require very lot of precision in manufacturing, because the tolerance that you need to have only about 0.001 mm, something like that. Okay. So therefore, even if it is offset by more than the tolerance level, the entire characteristics will change now, and it cannot be usable. We can't use it at all. Okay. So therefore the manufacturing process becomes costly. Okay. And then assembling cost also become more. Okay. So therefore all are quite expensive, but also, the development takes more time. Development takes more time because you have to, take a lot of pain, and you have to go through several trials to before you get the final version of the antenna. So therefore that is one reason actually why this happens. Okay, so now the another reason is actually the hardware integration of millimeter wave front end subsystem. We require very low loss and very cost effective interconnects, because we have to combine them into several things. The packages are to be assembled, so therefore all that becomes quite costly, and also the interconnecting lines. That means one module to another module. Typically, you'd have heard of it. There is a very popular subject area called VLSI interconnects. Okay, which works at several gigahertz of frequency, smaller in dimension, of several right. So when you are talking about monolithic microwave integrated circuit, all these things actually come into picture. So the interconnect lines, okay, those may be inside the chip on, system on chip kind of an application which works at high frequencies for digital circuit. But whereas here I am talking about interconnects which connect from one module to another. For example, I want to connect a mixer to low noise amplifier. Okay, typically in the front end, after the antenna, generally we'll have low noise amplifier followed by a mixer. Okay, so mixer will have one input from the low noise amplifier, another input from a local oscillator. So therefore, the mixer gives me an intermediate frequency called IF by beating the signal from the amplified signal from the antenna to low noise amplifier and the local oscillator. Both are mixed in the mixer, and then you get IF. Okay, right. So therefore, there we need to interconnect various modules. So what do you use to interconnect them is again a question, because they are actually available in smaller dimensions. So these becomes, a bit of very expensive structures, and also they should offer very minimum loss. Okay, so that signal can be generated as well as, it can be passed from one module to another module. So these are the real hardware challenges that are typically faced by the antenna designers. Some of these things are very evident to you when I show you some of these photographs and designs a few minutes from now. You will know that why these are, very hard to realize, and why it's a real challenge. Okay. Now, the millimeter wave antenna systems for mainly the future fifth generation application, because I already explained to you that these antennas are used mainly for the cellular and satcom applications. Okay, and of course for military applications. Okay, so and also we use for some other applications, automotive, and anyway, in the afternoon session I'll talk about applications of millimeter waves in automotive and military applications. Now, in this session, I'll show you some of the antenna designs for 5G applications. Okay, so now we know that the 5G is almost there, and then we are using other countries started using prototypes of 5G. Some systems, some areas started using 5G infrastructure for cellular purposes, even though it's not integrated and not into commercial stage in our country. But active research is going on various designs of 5G, especially called 5G NR. It is called 5G new radio standard. Okay, and there are various architectures. Okay, and there are various things that 5G gives us. Okay, so therefore the millimeter wave frequency is actually a very pre-standardization favorite for portable 5G applications. Okay, that's the only the reason why researchers are concentrating on trying to design the antennas and other structures using millimeter wave frequencies, because fifth generation depends on the millimeter wave frequencies mainly. Okay, so therefore that's why it is called pre-standardization, which is favorite for 5G application. That is one important point that we should understand here. Also, millimeter wave devices performance, we need efficient low profile antennas. As you see here, we need, I talked about just now, low profile is one of the important characteristics of the antenna. So therefore we need a very low profile, because smaller in size and weight, so for portable applications and for example, cell phone, you want a cell phone. For cell phone, what you need is a very low profile antenna, small antenna to integrate into your cell phone, device. And yeah, as you know that the cell phone size is becoming smaller and smaller, okay, as you go to the higher generations. So as I told you, in 5G, once it is fully into operational, once fully into operational, you may actually see a 5G cell phone of the size of your visiting card. Okay, and it's going to be true in the coming future, because of the latest semiconductor technological developments of having transceiver designs at 5G frequencies. In future, maybe after a decade or so, we will see maybe latest mobile devices of the size of your visiting card. Okay, so I'm actually very clearly pronouncing size of a visiting card means it is roughly about roughly about, okay, 7 centimeters by 4 centimeters of the thickness of about, all right. So such things are going to come in the future. And also 5G and near 6G, that people started already making some kind of a predictions for 6G, and they say that in future the mobile phone, since we are talking about foldable kind of a design, flexible electronics designs, okay, what they predict is that the 5G or 6G fully developed phone can be rolled, or it can be folded and put in your pocket. Okay, so that kind of a designs that are going to be very, very true in the future. Okay, going to be very true, and we will all will be in future. People will be carrying very, very paper like phones. Okay, that's going to the future anyway. Requirement of increased power, large bandwidth, and then a very high gain and insensitivity to the human user presence. There are actually, these are some of the things which complicate the antenna design, and also the propagation effects, because the attenuation is more when you go to higher frequencies, because the wavelengths are smaller. Okay, atmospheric attenuation, attenuation through rain, attenuation through all these things will be very much higher at high frequencies. So that's the reason why, as we move to the high frequencies, while we can have smaller and compact devices operating at maybe low powers, but we have this major problem of signal getting attenuated. Okay, as the distance increases, the signal get attenuated more, especially in the what do you say, the path loss, okay, will be more. Okay, power received also generally will be more. All right. So therefore, millimeter wave systems, however, they are designed using various techniques like multiplexing, okay, interference mitigation, scheduling, and radio resource allocation. So therefore, all these designs are now into fully 5G applications. There are various, I will not go into the details of 5G, 5G design, okay, 5G, what do you say, circuit design into waveforms and things like that. I will not go into those details. That's a separate huge subject altogether. But however, these are all linked to the antenna that we design for the application at, future 5G. Okay, so this is one thing that we all have to appreciate, the significance of millimeter waves for 5G applications and how critical it is to design systems, both hardware as well as the antennas fully, when it has to be integrated into a very small miniature 5G cellular phone, how complex it becomes. Okay, so you all have to appreciate that this is the complexity that lies in millimeter wave designs. Okay, so as you know that it's a new upcoming area, 5G. There are various simulation techniques. There are several software tools that we use, because we know that before we actually, build the, hardware, we always do a lot of simulation. Okay, there are some of you may be knowing there are several packages like HFSS and 3D Studio, okay, and then IE3D. So there are these tools we use for design of antennas and also other subsystems, okay, at a high frequency. So therefore, we need to have very high frequency simulator tools before we actually, build the systems. So therefore, what we need very novel ideas, new ideas, and then we need some kind of an innovative solutions, so that antenna design and system development can become much easier. Okay, so the current research trends, which I'm going to show in next half an hour or so before we close the session for today. So I'll show you some of the current research trends and some of the novel approaches. In fact, as I told you, a lot of work has already been done in this area in millimeter wave design. Okay, in fact, we can actually conduct one full 10 days FDP only on millimeter wave design. That much of even if you conduct a full day, FDP on millimeter wave designs of various aspects, including antennas, that we'll be covering only about 10%. We can't even cover that much of, growth has already been taken place, and it has already been developed in the millimeter wave area. Okay, so mainly, there are novel approaches, or several new ideas have come, mainly to address the issues of antenna design and also the propagation, and for the 5G, fifth generation enabled millimeter wave applications. Okay, so some of the approaches are, new antenna designs have come, new measurement methods have come, and then MIMO antenna. In fact, there is something called massive MIMO antenna designs have come. Okay, and also several beamforming techniques have been implemented. Okay, and also there are several solutions proposed for advanced millimeter wave operational scenarios. Okay, operational scenarios may include device to device communication. Okay, device to device communication means, as I told you, IoT device communication. Okay, so when they communicate using millimeter waves, that's called device to device communication. So that is one particular operational scenario. Similarly, multiplexing, spectrum, cognition, like intelligent radios, software defined radios. Okay, they use several such intelligent techniques. Okay, cognitive radios, and also in the areas of interference mitigation. Okay, so in all these things now, several new techniques have been proposed, and people are working in a lot of these areas. Okay, people are working in a lot of these areas. Okay, to address many of these designs. Okay, so now I'll show you quickly some of these designs for you. Millimeter wave 5G antennas for smartphones. Okay, one or two designs I'll just show you. But as you know the 5G mainly, these are some of the major things that we want to achieve in 5G. These are called key performance indicators. Okay, key performance defined by International Telecommunication Union. Okay, like IMT 2020 standard. So one is actually peak data rate. We want gigabits per second, and user experimental okay experience, user experience data rate, then spectral efficiency, then mobility as is shown here, then latency, then you have the connection density, number of devices within a square kilometer area, and then network energy efficiency, then area traffic capacity. You see here, these are all the key performance indicators for 5G. So it has to take care of all these things. So what I'm trying to tell you is that the millimeter wave design in antennas as well as in system design should actually address all these aspects. Okay, so therefore, key requirement for 5G is a 1,000-fold capacity, and now we know that there is something called a Shannon's capacity, by which for a given channel, now those who are familiar with the communication background, they will know the Shannon gives the ultimate final limit of how much data rate we can achieve in a given channel. Okay, depending on the signal to noise ratio and the bandwidth. That's actually Shannon's capacity, and that we have to look in a different direction here. Like channel capacity C is given by number of access points, or and the bandwidth multiplied by number of antennas M, and multiplied by log 1 plus SINR. This is actually not signal to noise ratio, but signal to interference noise ratio, SINR, interference mitigation. So therefore, in the light of this, now we have to check how much capacity. Now C is in gigabit or megabits per second. Okay, so therefore, as you see from this diagram, spectral efficiency, spectral extension, and network density. Okay, if you see this as my three-dimensional space, that if you want more capacity, or if you want more density, or if you want more topic, now you have to see what kind of techniques one must use. Okay, so we must use small cells technique. We must use high and wider frequency bands. We must use, and then we should use traffic offloading, 3D or massive MIMO structures. So these are all the requirements for the 5G. Okay, so this is one particular example I am showing you. 28 gigahertz antenna solution for 5G cellular communication. Okay, this is one particular example, one particular antenna design I am showing you. So as you see here, this is our cellular phone. Okay, now the cellular phone, let us say this is the direction in which, so the cellular phone has a built-in array, as you see here. This particular example that I am showing you, a 28 gigahertz antenna, how it is integrated into a cell phone is what I want to show you. Okay, for I see edge-based antenna array is the design for diversity, and data streams for MIMO design, and then beam steering is also achieved in the XY plane, and two different polarizations. Okay, so antenna type, this is a cellular standard. We have one antenna. It has in fact two antenna arrays, because all your 5G phones should actually communicate in all the directions. Okay, in all the directions. So the antenna design is complicated and integrated into the cell phone. So it implies what is called an antenna array integrated into the cell phone device. Okay, so therefore, as you see from this table, array configuration details are there here. 28 gigahertz antenna array configuration for 5G cellular, and its comparison with the 4G standard. As you see from this diagram or from this table, sub-wavelength antennas, and 4G is sub-wavelength antenna type, but for 5G, it is actually phased array antenna is what we have to design, which is integrated into the mobile phone. Similarly, radiation pattern is generally omnidirectional in 4G, but whereas it comes to 5G, it should be directional fan beam. What you see here in this diagram, this is actually called directional fan beam. Means what? It is in this direction it is communicating, and also it can be scanned. The direction can be scanned. Okay, that means if I have a tower in this direction, So the antenna points in that direction. Sorry, the beam is steered in that direction. Antenna is fixed only. It begins, since it is an array antenna, the beam can be steered in the direction of the tower or in the direction of your transceiver at electronic speeds. Okay, within milliseconds we can steer the beam. Okay, so it's not mechanical steering, but it's an electronic steering which happens at milliseconds stage. And also diversity and MIMO. In 4G it is used, and 5G also we use this. And polarization generally single constant, but whereas here we use multiple and reconfigurable polarization is what we use. Okay, so therefore the kind of array is also reconfigurable antennas that we use. Okay, so these are some of the antenna radiation patterns that you see in this, where 0 degree and then 45-degree tilt angle, how the radiation thing, and then 90-degree tilt, how the radiation pattern can be steered. Okay, these are some of the examples. And this is the photograph. I mean, this is the concept, but actual antenna is this. Okay, actual antenna is made of microstrip line mesh. It is called mesh grid patch design. Okay, mesh grid patch design, and it is 28 gigahertz mesh grid antenna array that is designed. And you see here, it's a 10-layer PCB of FR4 substrate. Okay, with this is a dielectric constant, and height is, you see here the dimensions, they're all actually micrometers, not even millimeters. You see here. So as you see here, some of the dimensions here, the H, L, various dimensions are shown. This H you see here, so H is only about 512 micrometers. Okay, so that's the kind of thing that we are talking about, which is actually designed and fabricated inside this one. Inside this, and microstrip feed is what is used here. So that kind of an array is designed, and then as you see in this photograph, in this diagram here, the second diagram, see, it is integrated into the side of the cell phone. Okay, that means here somewhere here. Okay, integrated into the cell phone. So 28 gigahertz mesh grid array. The C is actually, this is a top view, B is a side view, and and then you see is actually the phased array configuration. Okay, this is called mini SMP pads. Okay, and this is actual the thing that you see here. Okay, and also shown here a conventional cellular antenna and millimeter wave 5G antenna. Okay, as you see here, we have the ground and antenna structure on a PCB, but whereas here it is actually integrated with along with the RF circuitry. Okay, so this is a board, but whereas this is an array antenna. That's the difference between the 4G and conventional cellular. Sorry, not 4G. Conventional cellular antenna of 3G and this 5G. Okay, so these are the design that you actually see in terms of the thing. And as you see in this, this is a top view. Now this is a cell phone, for example. Now you can see an array here on top, an array here on bottom. Okay, so therefore this is a top view of 28 gigahertz mesh grid patch antenna, and these are some of the characteristics that like return loss, reflection coefficient, and all that. So this actually is a photograph of the millimeter wave 5G antenna. Now you see that it is integrated inside a Samsung cellular phone. Okay, and now it is zoomed and then shown to you that how does it look like. Okay, so this is how the future designs will come. And these are some of the characteristics like simulation and practical results. Like as you see here, they are nearly matching. And of course, I will not go into details of all this, but those who are doing into antenna design research, you will be knowing all this. That this is angle versus gain, and then angle versus beam width and all that. So therefore, the antenna beam and typical gain of the entire array of 16 element array that is shown here is 15 dBi. 15 dBi with respect to isotropic antenna. That's a gain that is shown over there. Okay. This is one design, and this is another design that I'm going to show you quickly. This is called a mesh grid phased array antenna design, but it has a reconfigurable horizontal and vertical polarization, but designed at 60 gigahertz frequency range. Okay, 60 gigahertz frequency range. So this is the design. As you see here, it's an array. Okay, which shows you the various, right? The when you change the angle, bore side tilt angle, like 30 degrees, bore side minus 30 degrees. That means when you tilt the thing, how much the gain reduces. Okay. For example, in the bore side, in the main axis of the antenna, it is 12.5 dBA, but reduces to 10 point something and 5 or 8 point something when you tilt into 30 degrees. So I'm sorry, the clarity of the slide is not that good. Right? So therefore, when you actually tilt, or when your hand is present, okay, when you are holding with your hand, due to presence of the hand, you see here, effect of the user's hand or millimeter wave. So due to the hand, the pattern of the antenna also may have some change. That's the reason why generally they don't integrate the antenna into the body, but only on top and bottom, because usually we hold the cell phone like that, where we don't generally hold on top and bottom. So therefore, it can radiate and radiate in this direction. Okay, so that is the thing. Like as you see here, the antenna main beam steering in the XY plane. Okay, so therefore, beam steering is one of the technique employed in the 5G millimeter wave antenna, where the beam is steered towards finding the nearest tower or the nearest transceiver or base station to catch the signal. Okay, so due to this, the beam can be steered from the design that I have shown here. The beam can be steered as you see here. Beam steering is only performed along the horizontal plane. Okay, so therefore this is comes under a multi-channel MIMO antenna design. That is what I am showing here. So we have one. This is the XY plane, and from the side, if you see, there will be one antenna array here on one side of the cell phone, and another antenna array on the other side of the cell phone. So what you see here is a fan beam. Okay, so that it can actually find the in both the directions. Okay, similarly, this is a photograph that is showing you the how the antenna is integrated into the generally. Okay, so in addition to this, we also have like this is a conventional thing. The diagram that is shown here in the left hand side is a conventional, like our 3G phone, okay, or a 4G phone, where I have one antenna for Wi-Fi, one antenna for secondary LTE or 3G, another antenna for Bluetooth, and so on. They're all different antennas. But whereas in a 5G phone, as you see here, we will not have all these antennas that are shown here. We'll have only one antenna here, which actually uses what is called analog beamforming technique. And this antenna actually gives me a fan beam on this side and a fan beam on this side. Okay, so this is the 5G antenna, which will be fabricated into the cell phone on just one corner. Okay, whereas this diagram is a conventional 4G phone, but whereas this is actually your 5G phone, where antenna is fabricated into the body in one on both the sides. Okay, so this is one of the configuration that we see here. Possible configurations like we can have one antenna or we can have two antennas with some kind of a reconfiguration. Reconfiguration means what? The antenna can be switched in and out. Okay, so I have a transmitter here, receiver here, and with a SPDT switch, single pole double throw switch. Okay, we can connect the antenna to transmitter and receiver, and using a double pole double throw DPDT switch, we can connect one antenna to transmitter, one antenna to receiver, or we can interchange. Okay, so like that. These are the designs that are going on. Okay, and this is the now this is an antenna design consideration, but actual antenna that you see here is this is actual antenna, where you see here there are 12 layers of FR4 PCB used. Okay, there are 12 layers of this is used, and hence you can easily see that now you can see the distance that is there between each of these layers of the design. Okay, now as you see here, the diameter and 12 layer PCB is what you see here, and this is actual antenna of 12 layer PCB, and there are layers like M1 to M12. Okay, each layer has its own line. You see here, and the feed line is here, as you see here, which feeds energy from this RFIC, from the transceiver circuit. So the entire thing is now in 12 layers. Okay, RF power input output. Then there's a common thing of ground. Then you have micro SMA connector. Okay, SMA stands for sub-miniature A type. Okay, usually SMA, SMC connectors are used, but smaller connectors there is actually micro SMA connector. All right, you see here. So this is a design that goes into the latest 5G at 6 gigahertz radio frequency IC integrated circuit with 8 RF chains in flip chip mounted on layer M1 and so on and so forth. Some details are given here. Okay, how this works. Okay, and so this is the typically the side view. This is called horizontally polarized thing, and this is a vertically polarized hand. I think somebody has raised the hand. I can take the questions in the last 10 minutes. Let me complete the presentation. I see a hand raising by Mr. Ajit Kumar Singh, but I'll take up the questions in the last 10 minutes. Okay, so as you see here, these are the designs that go into your cell phone with a fan beam that you see. This is a horizontally polarized one. Next slide shows the vertically, horizontally polarized, and its beam it is being shown here. The next slide is showing a vertically polarized 60 gigahertz antenna element with a beam steering implemented. And of course, anyway, it takes very long time for me to explain each and every detail of this slide. But however, you can appreciate the kind of designs that people are working with, which goes into your latest 5G cell phone, and how does the beam. This is the antenna that is included in the side of the antenna. The cell phone. Okay, this is for the vertically polarized design, and it's the typical radiation pattern that you see here. I told you half hemisphere is the radiation pattern that you see here, and typical with the beam steering implemented. So because beam steering is one of the techniques which is essential for 5G mobile phone to work, because it has a fan beam and it steers the beam to find the right direction of the cell tower or nearest transceiver to catch the signal. Okay, so beam steering is implemented by default in 5G phones and 5G millimeter wave antenna that is designed. Okay, these are some of the characteristics of VSWR of the antenna. I will not go into details of this. And typically, this is the thing that is shown, the actual antenna. As you say, vertically polarized, horizontally polarized antennas are kept side by side. That means this diagram, whatever I am showing here, is nothing but the minimized version of the antennas that I am showing in this two. This one horizontally polarized, and this one is vertically polarized. Okay. So this antenna, that is a single antenna, is what I've shown, but whereas here it is being shown as an array. Okay, as you see here, the blue ones are vertically polarized, and the red ones are horizontally polarized. They're all interconnected by the feed line with a 12-layer PCB into your okay. Okay, so this entire design, as you see, it's only by 15 by 7 millimeters. See here, it is a phased array design that I'm showing you here. 15 millimeter. 15 millimeter means just 1.5 centimeters. And this is about 7 millimeters, okay? Just 0.7 centimeter. So the entire design is only that much. Okay, and it is integrated into the millimeter wave. The millimeter wave 5G antenna is now, once it is fabricated like this, it is integrated with your digital circuits in the cell phone with all these three. There are three types of integration mechanisms. Okay, by this it is integrated into the actual design. Okay, that is the second design that I have shown you, and this is another thing called instead of one beam, there are also technologies with multi-beam. So that means they generate several beams, several beams like this 1, 2, 3, 4. It generates several beams and then radiates simultaneously. So when there are several beams generated, now this can communicate with a tower in this direction, tower in this direction, and also these beams can be switched. They are actually called, massive MIMO designs of generating several beams. Okay. So these are the architectures. I will not go into details again, but as you see here, there are active circuits with a low noise amplifier and power amplifier and mixers with a local oscillator included here. And these are the ways. Then we have RF transceivers, and then we have phase shifters here, and then we have the balanced thing here, and then antennas. Okay, this is actually several antennas are there in an array. Okay, this is architecture, passive and active multi-beam patch arrays. Okay, MBPA, multi-beam patch arrays are what are used. Okay, with some phase shifters. There are two designs are used here. One is a passive design, and the other one is called active design of multi-beam patch arrays, patch array antenna (MBPA). The difference between passive will have low noise amplifier and this here, but whereas active design will have the low noise amplifier, power amplifier after the mixers. Okay, so just before the antenna we amplify and radiate, and through a low noise amplifier we receive the signal. Low noise amplifier receives the signal from the antenna, power amplifier sends the signal to the antenna. So this is you see the direction here. Low noise is inward towards the receiver, and power amplifier is towards the transmitter. Okay, so therefore we have several antenna arrays like this shown in the photograph here, which are integrated into the the final device that we use them. Okay, and this is a micro photograph of a quad beam 2 antenna KU band design. KU band is actually 18 gigahertz. Okay, designs. So these are the multi-beam designs that are available to communicate with the users. And there are several challenges whenever you want to design multi-beam antennas. One is the beamforming algorithm challenges are there. Highly efficient baseband algorithms are required, and that is for the proper direction of arrival. From which direction the beam is coming, it has to identify, then switch the beam in that direction. So therefore, we need a very high-speed direction of arrival algorithms to find the direction from which the signal is being received. And also we need a digital beam multi-beam antenna is desired. So this is one challenge is regarding beam forming algorithm. That means how do you steer the beam, how do you form the multiple beams is one challenge. It is because you have to find out DOA. Then the challenge is digital processing of hardware challenges. Okay, that means once you get the signal, how do you analyze, how do you take several channels of RF, because you need to actually service several users, okay, of 5G users. Hundreds and thousands of users you have to serve at simultaneously from the tower. So therefore, how do you process and then finally get the baseband? Okay, and we need a very high speed analog to digital and digital to analog converters, and we need a very high speed DSP chips with a very high throughput, because we are talking about several gigabit per second rate that 5G gives us. Okay, so therefore we need very high speed, high throughput DSP capabilities are required. Okay, and digital beam formers are required to form the beam and steer the beam and generate the beams. This is another challenge. The third challenge is millimeter wave components themselves. Okay, like multiple users use multiple independent beams. Remember, the 5G technology offers one beam from each user. Okay, this is a very unique characteristic of a 5G technology. If I'm using my mobile phone, okay, there is a separate beam dedicated for me from the tower only to me. Okay, that is called multiple user using multiple independent beams. Okay, if there are 105 users around the tower, 100 beams are generated. Okay, it is because one beam is dedicated for me. I am getting a very high throughput of gigabit per second speed, otherwise I will not get. That's the main difference between the 4G and 5G. Whereas in a 5G and 3G, we have one single antenna beam serving thousands of users in a given direction, or 100. But whereas here, multiple independent beams are generated for each and every user separately. If I have a 5G phone in my hand, I can independently communicate to the tower with a single beam. Remember this very particularly. That's a one of the important characteristic of a 5G design, generating multiple beams. Okay, so therefore the signal to noise ratio is very much better for me because I have my own beam. Okay, so therefore multiple beams are generated by the tower as well as by my cell phone. Remember this. Okay, so therefore that's why I have a multi-beam design also in the device. So therefore good linearity, power efficiency, thermal control, all these things are part of your design, part of your millimeter wave component. So these are the challenges. Similarly, the fourth challenge is array channel challenge. I have shown you some one array design just now. How you design an array, antenna array, and how do you have? Sorry, it's not about antenna. It's about channel of array of channels, RF channels. Sorry. So how do you couple these channels? How do you avoid mutual coupling between channels? How do you maintain synchronization? How do you collect the data? So it's very complicated. So therefore, what we need is called channel synchronization by delicate algorithms are required. So these are the various things. And the fifth challenge is system implementation challenge. Okay. Finally, to implement. So we need a very compact and multi-layer PCB. Just now I shown you 3 designs of multi-layer PCB. multi-layer PCB configurations are difficult to implement. So there is a challenge because a lot of precision is required because you are talking about micrometer level of thing. Okay, limited board area because you want the device to be very smaller, and you need to encompass all the transceiver chips, okay, into the design, and very closely spaced antennas, making signal routing becomes difficult. And we need a very optimized balance between the performance and complexity. Okay, if you want better performance, complexity increases. But if complexity increases, the device cost will increase. Okay, and so therefore you have to strike a balance between the performance and complexity. And also, how do you realize a millimeter wave chips, transceivers, receiver, transmitters, receivers, filters, mixers, okay, and all this. Okay, these are the challenges. Okay, so I've shown you three very complicated designs. I talked about various challenges in generating, such things and integrating. So there is another this concept called self-alignment, because we need a very perfect alignment between the beams. Then only they can communicate, because the beams are very, very narrow and sharp. So therefore, we need a very good alignment. So typically, millimeter wave antennas are aligned. For example, this photograph shows a backhaul point-to-point link, okay, using 5G small cell implementation. So when we have 5G towers implemented at various places, they are basically implement for 5G technology deployment. We use electrical poles. We actually put 5G transceivers on the integrated with electrical pole. We don't see a big tower in a 5G technology. We actually mount them on buildings. We mount them on street poles, and we mount them wherever we find on trees. For example, we can mount. That's how we deploy 5G, not like big towers. Okay, and the companies will operate using backhaul point-to-point links as shown in the diagram. Okay, but for users, the 5G will be very near to them. Okay, so typical distance, as you see, 100 meters to 10 kilometers. Okay, typical distance. High data rates are 1 to 20 gigabits per second. Gigabytes actually. Capital B is bytes. Small antennas are 120 to 600 mm size. 120 mm is 12 centimeters to 60 centimeters. Smaller antennas are used, and then that's how they connect the intra offices. Okay, through that they actually give service to the users. And as you see, industrial sites and campus dedicated links. And these are some of the parameters, some of the frequencies. I will not go into more details, but as you can leisurely go through this. What is the frequency band? What is antenna diameter? It is 30 centimeters. What is the antenna half power beam width? What is antenna gain? Transmit power, how much? What is the gallium arsenide transmitter is used for amplifier? And then how much power? Typically 20 dBm is 1 watt. 1 watt of power is used. What is the distance? 12.8 kilometers. Atmospheric, remember I told you atmospheric attenuation. How much attenuation will be there per kilometer? How much is the received power that you receive? Okay, of microwatts. And these are the various parameters like 38 gigahertz band, a V band of 57 to 66 gigahertz, and then V band of 38 dBi, and then E band 71 to 86 gigahertz. So these are the various design parameters of a given millimeter wave link that is used for connecting, and typical antennas that they use for a given application. Okay, so this is the type of antenna, V band antenna, 30 centimeter, small form factor. They use such antennas on that. Okay, all right. And similarly, transmit array, different kinds of. You see all these tiny dots you see are array, small elements. Okay, this becomes your transmitter array. Okay, this is called an array. And several electrical characteristics of the antennas, several mechanical characteristics of the antennas. Okay, that means what kind of material, dimensions that we use, how much is the weight, what is the temperature. These are the mechanical characteristics, and these are the electrical characteristics: VSWR, gain, 3 dB bandwidth, polarization. All these are millimeter wave antennas for long haul, backhaul. Some of the radiation patterns of the antenna. You see the beam is very, very sharp. It's a pencil beam actually. So the pencil beam has to be aligned between the transmitter and receiver. Then only they can receive. Okay, and like this. Now let us say self-alignment. They use a self-alignment technique. Okay, so that the beams are perfectly aligned. Let's say this is one tower and this is another tower. They are aligned like this. You see here. So there is a lot of work. Antennas have to be very accurately point to each other. Then only they can transmit and receive the signal. Okay, that's how the links are maintained. The proper links are maintained so that they can send and receive the signal. So on the rooftops, usually they maintain. This is a photograph I have shown you. This is the thing that I'm talking about. This is a rooftop. These are the towers that I'm talking about just now. Okay. So they are aligned at millimeter wave, frequencies. Okay. Yeah, and some points on the beam forming. As I told you, beam forming is very critical for utilizing millimeter wave channels. And some of the beam forming basics, I will not spend more time here. Those who are into the antenna, they will know how the beam can be steered. This is a theory again, so that's why I will not spend more time. This is an antenna array theory to how the beam is formed. So when you have several antennas here, by changing the phase between the individual antenna elements, we can now steer the beam. For example, this is the beam. This is the direction in which the beam is changing. By changing this phase between the antenna elements, now this beam can be steered from this to this direction. Okay. So the principle of beam steering or beam forming is by changing the phase shift between the individual antenna elements, like when they are in array. Okay. So when they do this, and we can actually have some network to sum the signal from the array. Okay. So this is a kind of a beam pattern you will get. This is called the main beam. All the small things are called side lobes. Okay. Typically we get a very, very sharp beam. So what I'm showing you is the antenna beam pattern of a 16-element array. How the beam is formed. These are 0 degrees. But if you want to shear the beam to, let us say, 3 degrees, then by changing the phase shift, I can steer the beam to 3 degrees. So generally, bigger antennas, they are physically rotated to steer the beam. But whereas these phased arrays, we can electronically, by changing the phase between the element, I can steer the beam. No physical rotation involved. No physical rotation. It's only electronic steering. Okay. You see here. Now, pattern of 16 element, lambda by 2 spacing between the elements. Now, see the beam. Now, when you change from lambda by 2 spacing to lambda 16 element array with lambda by 2, but with a different phase. But now the beam is sharp. Okay, like that we can do. Okay, so digital beam forming uses several antennas, as I explained to you. With that, we can have millimeter wave antenna array can be employed. We can have up converters and then the digital to analog converters in the digital domain. And then we can use the phase shifters here. It is called RF beam forming. Okay, radio frequency beam forming. And also we have technology called 5G with massive MIMO. Okay, not just MIMO, but massive MIMO. Okay, this is a new technology that they are being deployed. Massive MIMO technology promises revolutionary improvements in network capacity, data rates, latency, and network flexibility and efficiency can be improved. Okay, so 28 to 59 gigahertz or 39 gigahertz are used. So therefore, massive MIMO also has one example I'm showing you now, millimeter massive MIMO lens antenna array for 5G application. Okay, so these are some of the antenna requirements that we need a beam shaped antenna. Okay, and then this is the principle of massive MIMO. Okay, it uses hundreds of base station antennas to simultaneously serve multiple users. That is called massive MIMO. That means at a single location, we'll have hundreds of antennas are used so that we can serve multiple users at the same time. Now, as I told you, that we'll have independent beams and several hundreds users, thousands of users to be served. We need multiple beams to generate one beam from each user. So we use a concept called massive MIMO, okay, technology. And that uses this. See, for example, this is one base station, but you see several antennas are there here. Okay, so they generate several beams. So therefore, each beam is serving one user. Okay, user 1, user 2, user 3, user 4, like that. So this is called conventional MIMO. What I am showing here is a conventional MIMO, okay, technology, LTE. Current 4G is using this, but now in massive MIMO, you see number of elements, 100 to 1000. Now here 2 to 8 antennas are only used, where M is the number of antennas here. Okay, 2 to 8 antennas, whereas here 100 to 1000 antenna elements are used. Okay, and antenna, okay, number of users who can know how many can be served. Okay. LTE, but here it is now. See, several users can be served simultaneously. Okay, so this is called millimeter wave massive MIMO technology. Okay, dozens of devices are used. So they will have large non-monotonic path loss, and millimeter wave antennas are small, perfect for massive MIMO. And of course, channel estimation and system complexity increases, but however, we can use them, no problem. Okay, yeah, yeah. So therefore, now these are the bands. These are the three properties, mainly advantage of using millimeter wave massive MIMO. One is high frequency, short wavelength, and of course, path loss is serious, but it has to be handled in a different way. Okay. So high frequency, short wavelength, and serious path loss, millimeter wave. So therefore, there are some techniques to mitigate that. We can use large antenna array, but we can use small cells to reduce the path loss. Spectrum expansion can be done. So this is the antenna, lens antenna array that we are talking. One example, that there's an array here, okay, conventional MIMO, whereas here beam space, there is a lens used here. So from the conventional array, the beam is focused now here, okay. So as you see here, we have digital processing is done here, and then we have RF, and there is a lens antenna array implemented here, so that I can generate multiple focused beams. That's it. Conventional MIMO is this, and then beam shape MIMO is this. That's a main difference between when they use an array, multiple beams can be generated. This is a typical prototype of the actual antenna, and 16 elements are used in that. 16 elements are all these are 16 elements. Okay, these are the elements. Okay, these 16 elements are used with a lens. We can have more focused energy. Okay, and of course, all these details will be there. Okay, so this is another example. I think last example, 77 gigahertz millimeter antenna array on a different technique called liquid crystal polymer. I was telling you that so far I have shown you microstrip design. It is on the liquid crystal polymer for automotive radar and RF front-end module. Automotive radar is, afternoon I'll talk about automotive radars for automobile application. They use this, okay. Typical low-cost antenna, okay, compared with the low-cost substrate. Typical 16 by 16 element antenna array is what is used here. But as you see here, these are the several antenna arrays that are used here. And, these are the several microstrip on polymer are used here. They use a coplanar waveguide line bends to connect the antenna elements. This is a system integrated. Millimeter wave microstrip array is integrated on top of this. And I have a low-cost millimeter wave RF substrate. On that antenna structure is this is the antenna structure. Okay, and there is a feeding given to this structure, and there are other circuits like DSP and all at the bottom of the substrate. Okay, so this is one example of the design, and this is a more clearly shown how the antenna element is integrated and how they are shown. Okay, this is the photograph of, for example, this is a 8 by 2 array. I have got, you see here, there are 8 elements and there are 2 rows. So it's an 8 by 2 array, okay, and this is a fabricated antenna under test. Okay, this is each element like that. There will be 8 elements here, and there are 2. Okay, 8 by 2 array, and this is a photograph that is actually showing the antenna type. Okay, and these are the respective beam shapes. As you see here, simulation and the results are matched. Okay, so that's all. This is how it is integrated finally into that, and typically in an anechoic chamber they test this antenna once it is fabricated, and this is a typical structure on which it is mounted and fabricated. Okay, so I think that's the last slide. That's all for today. So I tried to explain you the significance of millimeter wave antenna, latest structures used for 5G applications and for various other applications, communication and all that. Okay, so that's all from my side. If you have any short questions, I can now answer, and then then with that we can close the session. Thank you once again for your patient listening, and thank you for giving me the opportunity to interact with you and then explain you the technology frontiers of millimeter wave frequencies. Thank you so much.
Hello, sir. 2 questions are posted in the chat box, sir.
Okay, so if you can read out, please,
Hello.
I can answer.
Yes, sir. I am the reader. This question is from Dr. P. Surendra Kumar.
Okay.
Size a low-cost substrate. Size a low-cost substrate material at a millimeter wave band, which gives best antenna performance, other than FR4 and RT divide. Size a low-cost substrate material for a millimeter wave band, which gives best antenna performance other than FR4 and RTB5?
No, actually, FR4 is the lowest one because see, FR4 is not costly actually. For millimeter wave, out of the available materials, FR4 is the lowest one. Because for conventional, I mean, millimeter wave actually, as I told you, we have to use a multi-layer thing. Okay. Because of the thicknesses that are involved. Okay. Usually, out of all the materials, FR4 is the lowest in terms of cost, whether used for microwave frequencies or millimeter wave frequencies. I think, I mean, of course, your voice is a little bit disturbance, but I understood that they wanted to know the lowest cost substrate for millimeter wave other than FR4 not required. Is that right?
Yes, sir.
Yes, sir. Yes, sir.
They are asking for a straight.
So, see, actually, to work on millimeter wave, first thing is that cost is generally compared to FR4 at microwave frequencies. FR4 at millimeter wave costs very much higher. Number one, because of thickness involved, and also to work on millimeter wave antennas, we need special facilities which are very expensive. Okay. Even I don't think even IITs as on today have practical facilities to fabricate a millimeter wave antenna, except at low end of millimeter wave range. That means around 30 gigahertz. Okay, so therefore, out of all the materials, FR4 is only of lowest cost. Next question, please.
There is a question from Ramya Radhakrishnan. Hello.
Yeah, please.
The next question is brief about the significance of separately polarized antennas in 5G. There are separately polarized antennas helpful, especially with 5G application.
Correct.
Which 5G application can be targeted if one works with separately polarized antennas? I will read once again, sir. Brief about the significance of separately polarized antennas in 5G. Next one, there are separately polarized antennas helpful, especially with 5G applications.
Anyway, I think the voice is not clear for me. There's a lot of
Ramakrishna sir, let me read out, sir. Ramakrishna sir.
You can carry out.
Yes, sir.
Okay.
So, sir, the question is brief about the significance of circularly polarized antennas in 5G.
Okay, all right. See, actually, all our mobile phones they use circularly polarized only. Only the transmitters of the carrier providers, they only use horizontal and receiving devices. They use circularly polarized on most of the designs. Okay, it is because orientation of your device matters a lot when receiving a signal. So therefore, if you specifically fabricate only horizontal or vertically polarized antennas in our receiving devices, and we have to orient the devices in that direction towards the transmitter. But whereas if you have circularly polarized antennas designed, whether it is 5G or any other application, that irrespective of the orientation of your device, it can still receive the signal from the source, that is from the tower or from the transceiver thing. So therefore, all the designs, especially from the point of view of the portable wireless systems, we invariably find only circularly polarized designs. Okay, we don't find only horizontal or only vertically polarized. The main significance is this: apart from not orienting the antenna to receive the signal, there are other advantages of circular polarizations which are built into that. For example, the multipath propagation losses are less if you use a circularly polarized signal from the source. Okay, and fading losses are again less if you use circularly polarized thing. Okay, so it is because of these reasons of orientation issues, multipath loss, and signal to interference being less to mitigate the multipath loss. We prefer circularly polarized antennas.
The continuation of that question, which 5G applications can be targeted?
See, the main 5G applications are, one is the cellular is the main application for 5G phone is one. Other than this, actually, 5G fifth generation is used in some of these specific things. Specific things like, as I told you, like you have radars that are one is communication cellular, anyway, that is pretty well known to us. Other than communication application, we have the 5G band radars used in automotive applications. The second thing is a military application, okay, where it is generally exploited now. And some of the what do you say, customized communication, especially military communication they use. Okay, I mean, when they use 5G, since you are talking about 5G target applications, 5G target application for civil and military applications, they use civil application like crowd control, which I talked in the afternoon session. Military application like there's something called and anti-denial system. They use this. And then next most application is automobile application, especially in cars and other devices, drones, for example. Cars and drones, they use 5G radars for finding location, sending, receiving signals, and for finding obstacles, avoiding obstacle. For all these applications they use. These are the target applications.
Okay, sir. So, there is one more question, sir.
Yeah.
So, what is a new method to reduce mutual coupling in massive MIMO?
Okay, massive MIMO. Okay, mutual coupling. So when you talk about massive MIMO, mutual coupling reduction massive MIMO, we have to know first understand in which application. For example, if when you use massive MIMO for 4G application, the antenna elements, I mean mutual coupling between the systems when they use multiple antennas, we have got various techniques like shielding, and then techniques like multi-directional beamformers. Okay, that actually reduces mutual coupling, because I understood when you talk about mutual coupling is when you have several sources nearby, there'll be mutual coupling. Okay, so these are the techniques. And when you come to the aspect of massive MIMO 5G scenarios, generally mutual coupling is avoided by the high frequency shielding, because of the dimensions involved, which are very, very smaller. Okay, and you have to now understand the mutual coupling when you implement them on a system, or when you implement them in the RF front end. At RF front end, the mutual coupling is generally avoided by having between these channels, by having separators, or by having multi beamformers. But when you want to avoid mutual coupling on the system, there are special interconnects designed which can avoid the mutual coupling. So special interconnects are to be designed.
Okay,
Okay.
sir. So there is one more question, sir.
Yeah.
Can polymer-based substrates be used for 5G applications?
Yeah, they are being used. They are being used, but they are at the prototype and experimental level. Research is being done. Okay, one example I have already shown you, lens array and polymer. They are being used. Prototypes, designs are there. Laboratory designs and research papers are already there in the literature on this.
Okay. Thank you, sir. That's it, sir. There are no more questions, sir.
Okay, thank you.
Thank you so much, sir. Ramakrishnan, sir.
Okay then, if that is okay, then I'll just log out, and then afternoon we have a session on automotive. Some of those technologies I'll just show it to you out there. Okay. Thank you so much. Now please permit me to log out. Then
Thank you, sir. Thank you so much, sir.
thank you.
Ramakrishnan, sir. Hello, sir. Ramakrishnan, sir. Hello, sir. Sir, Ramakrishnan, sir. Can't able to hear your voice, sir. మీ వాయిస్ వినపడతలేదు, sir. So participants, the session is over. So you may leave the session now. So you can join the afternoon session by 1:50 p.m. Thank you so much. Participants are requested to leave the session. Thank you. Thank you so much.